Hello friends, today let's look at merge sort. Merge sort is a sorting algorithm which is very efficient, so it's widely used to sort a list of numbers or any list of items in the given order. To see the intuition of merge sort, let's first look at this cards example to see how the merge process works in merge sort and then look at the actual algorithm. Here we have four playing cards placed face up. These cards are divided into two groups. The first group has number 2 and 6 and the second group has number 3 and 9. So as we can see, these two groups are themselves in a sorted ascending order. Now let's say we want to merge these two groups in maintaining their sorted ascending order. So how would we do that? We will consider the first cards in both the groups 2 and 3 and pick up the smaller cards since we are doing a ascending order. Now we need to consider the next card in the first group since the first card is already picked up and the current card in the second group is still 3. So 6 is compared with 3 and again a smaller card is picked up. Now since 3 is picked up, the next card is the current card which is 9 in the second group and 6 is compared with 9 and the smaller card is picked up again. And now only 9 is remaining, so we pick that up and append it to our sorted card list. So here we saw that if we have two lists of items which are already sorted, we can merge them into a joint sorted list by going through both the lists simultaneously and picking up the current item which maintains the sorted order. That is, to create a sorted ascending order, we pick the current smallest item and append it to the joint list. Now let's look at the merge sort algorithm. Merge sort uses a divide and conquer approach to recursively divide the list of items into two equal parts, then sort the two parts separately and then merge the two sorted parts. For example, if we start with a list of numbers, the list is first divided into two halves, then each of the halves is further divided into its halves and so on until each part that is created has only one element or one number left. At this point, we can stop dividing the lists further and we can start merging them. So now, this part which has only one element left and this one will be merged together to form a merged sorted list. Similarly, these two parts will be merged together to form another sorted list. And now these sorted lists will be further merged to form a bigger merged sorted list. Now let's look at one more example to understand how merge sort works. Here we have a list of four integers 25, 10, 9 and 1. This list is first divided into two halves. So we have now two lists. First has 25 and 10 and the second having 9 and 1. Now these are further divided into halves. At this point, each of these lists are sorted. So now we can merge them to form merged sorted lists. So now these two lists having 25 and 10 will be merged to form a sorted list. And similarly 9 and 1 will be merged to form another sorted list. And now these two lists which are just created having 10 and 25 and another having 1 and 9 needs to be merged again. Now let's see how to merge these two sorted lists. We first start by comparing the first elements in both the lists like we saw in the card example and we pick up the smaller item which is 1 in this case. Now since we picked up the first number from the second list, the current number in the second list will be 9 and 9 will be compared to the current number in the first list which is 10 and we pick up the smaller one again, so 9 is picked. And now the second list is empty. The first list has 10 and 25 in the sorted order, so we can just append these two numbers to our result list. And finally we have 1, 9, 10 and 25 in a sorted order. Now let's look at the implementation of this algorithm in Python. Here I have defined a function called merge sort which takes in a list of integers to be sorted. This is a recursive function and it sorts the list in place. That is, we are not returning another list here. Also, we are not creating extra lists when we divide the list into halves. That's why we will need the starting and ending indices of the original list that we are working with. So we have another utility function here to call the actual merge sort function, which sends the list as well as the initial start and end indices. Since initially we consider the whole list, the start index will be 0 and the end index will be the length of the list. Inside the function, we divide the list into two halves by finding the mid, and then we call the same function merge sort for sorting the two lists. But we are not creating another lists here, and we are just sending the indices of the lists to be sorted. So the first list will go from start to mid and the second list will go from mid to end. For any recursive function, we also need to specify a stopping condition. So where do we stop recursing in this merge sort function? When we have only one element left in each part, as we saw in our examples. So here, this if statement takes care of that and it returns for the case where there is only one element left, and the rest of the code is executed only if that condition is not true. Then after the two calls to the merge sort, we have a merge function here which merges the two sorted lists. Now since we have not created another list, we are still sending the same list called list nums and specifying the indices for the two lists to be merged. And after this merge function returns, the list nums from index start to end will be a merged sorted list. Now let's look at the merge function. The merge function takes in a list of numbers, the start, mid and end indices. Here we create a new list which will contain the merged list. Then we have I and j, which are pointers pointing to the starting indices of both the lists. So I points to start, which is the starting index of the first list, and j points to mid, which is the starting index of the second list. Then we iterate through both the lists simultaneously using this while loop, I iterating over the first list and j iterating over the second list. Inside this while loop, we compare the current elements of both the lists and append the new list with whichever element is smaller. Now, if the two lists to be merged are of the same size, then we will be done comparing and appending the elements from both the lists at this point. But since these lists can be of different sizes, we will have to append the remaining elements from the larger list to our new list. Depending on which of the two lists is larger, one of these while loops will append the remaining elements to the new list. Now finally, we need to copy over the new list to the original list. Since we are not returning the new list, the list nums should contain all the elements merged from both the list in the correct positions. So this last while loop copies over all the elements in the new list to the list nums in the correct positions. Now we are done looking at the merge function as well as the merge sort function, which is a recursive function. Now let's look at the time complexity for merge sort. Let's first consider the runtime for the merge operation. In the merge operation, we iterate over both the lists simultaneously and we create a third list as we saw in our example and in the program. This takes time proportional to the total number of elements in both the lists. Now let's consider the recursion in merge sort. We can unroll the recursion to see the work done at each step. We start with a number list having n elements and divide it in two halves in each of the step. So in the second step, we have two parts having n by 2 elements each. Then in the next level, we have 4 parts having n by 4 elements each, and so on. Now let's see the time taken for the merge operation at each of the levels. At the top level, to merge n elements, the time needed will be proportional to n. In the second level, we have two parts having n by 2 elements. So each of these parts will need time proportional to n by 2, and hence the total time at this level will be again proportional to n. Similarly, at the third level, the time taken for at each of the parts will be proportional to n by 4, and the total time will be proportional to again n for all the 4 parts. So we see that at each of the levels, the time needed will be proportional to n, the total number of elements in the list. Now let's say we need k steps to reach from n elements in the number list to the last level, which has only one element per part. So since we are having k levels, and at each level we have double the parts as its earlier level, and each part will have half the elements as its parent, the relation between k and n would be n is equal to 2 raised to k. So from this we get k is equal to log of n to the base 2, and at each of the steps we need O of n time, as we saw. So the total time complexity will be O of n times log of n. So to summarize, merge sort uses a divide and conquer approach to recursively divide the list in halves and then sort the halves and then merge the sorted halves. The time complexity in the big O notation for this algorithm is O of n log n. So that's it for this video. Thanks a lot for watching.